Hello, in this video you and I are going to plot the root loci of a given transfer function.
The given system is represented by g of s, where g is 2 over 8s plus 1 times e to the power of minus 2s. Now, the first issue we have here is the fact that this system has a time delay, which in this case is 2 seconds. Root locus analysis can only be performed on rational functions. Therefore, we must find a rational approximation for the exponential part of g of s. A first choice would be a Taylor expansion, which is given by this formula. Here, we're going to make three adaptations. First, we're going to pick the evaluation point to be 0, because we want to perform the root locus analysis around the origin. We're also going to truncate the series at the second order term, that is to say, n must be smaller than 3. Also, our f of x in this case is going to be actually an f of s, which is e to the power of minus 2s. With all that in mind, we can transform this series into this, which is actually a Maclaurin expansion. Here are given the first two order derivatives of f of s, which allows us to calculate the Taylor series approximation for this exponential to be this function. Now, PADI provides us with a better approximation, which improves upon Taylor's approximation. What PADI says is that there must be a polynomial function of a constant k times s plus a constant p over s plus a constant q, which is equal to the Taylor expansion. By developing this function, in this case here, multiplying both sides by the polynomial on the denominator and rearranging the terms and then equating the terms on each side, the terms that multiply s of the same order on each side, we can get to a system of three equations and three unknowns. We also can just disconsider the third order term. With this, we can get to the values of the constants that we were after, that is p equals minus 1, k equals minus 1, and q equals 1, which we're gonna input in this formula and then use it to calculate an approximation for g of s. Now, with these values, we can plug them in the PADI approximant for the exponential. We get a final form of that approximant, which we use to replace the actual exponential in the original function of g of s. We perform this multiplication, and this is the final formula we get for the PADI approximant of g of s. This is the formula that we're going to use to perform the root locus analysis. The first step is to find the zeros and the poles of this function. So the zeros it's only one zero, and it's located at s equals 1. Here we have our first attempt in the complex s plane, and the zero is located at plus 1. The poles are located at minus 1/8 and minus 1. Now we can go to the second step, which is the evaluation of the angular condition. The angular condition says that the sums of the contribution of the angles of the zeros at each point minus the contributions of the angles from the poles at the same point must be equal to plus or minus 180 degrees times 2k plus 1, where k is a natural. Now, we're going to choose 4 points, one on each region of the real axis, which is divided by the poles and the zeros. And for P1, we're going to have that the angles of the zeros and the angles of the poles are 0. Therefore, the total sum is 0, and there is no such natural k that satisfies this equation. Therefore, the zone of P1 is out of the root locus branches. The same is not true for the points on the P2 zone. We can see that the sum is going to be minus 180 degrees, which is true for k equals 0. So if there is a k that satisfies this equality, then this area belongs to the root locus range. For P3, we see that the sum is minus 360, so there is no k that satisfies it. The zone of P3 is out of the analysis, and P4, which starts at 1 and goes all the way to the 0 at the infinity, is in, because k equals 0 also satisfies the equality. Now we can proceed to step 3, which is to find the break-in and breakout points. Break-in and breakout points are the points of the real axis where the root locus branches go away from the real axis and into the plane. So the places where they collide and go either up or down. In order to do that, we're gonna use the equation for the gain k, which is given by this. In order to simplify it, we're gonna multiply the numerator and the denominator by minus 1. After that, we're going to calculate the derivative of k in respect to s. In order to achieve that, we're going to use the quotient formula. Here we have our h of x being represented by our k of s, our f being the numerator, and our g of s being the denominator. After that, we are going to arrive at this k prime, which represents the first order derivative, equal to this function. By equating it to 0, we can solve the numerator, because the denominator is going to be disconsidered. We can just multiply both sides by this function, and the roots of this equation are s equals 5/2 and s equals minus 1/2. This is consistent because both these places are in the root locus branches and they are in the real axis. So these are the places where the branches collide and go either up or down. Now, this would be the time for us to find the angles of departure and arrival of the branches. But this is not needed for this transfer function because, as we've seen previously, all the poles and all the zeros are located on the real axis. That means the departure and arrival angles can only be 0 or 180 degrees. That, coupled with the fact that we know that each branch departs from a pole and moves towards a 0 as k increases from 0 to infinity, is enough for us to determine all the angles needed. So we go straight ahead to step 5, which is to find the points at which the branches cross through the imaginary axis. For that, once again we recur to the characteristic equation. But this time we're not going to find the derivative and make it equal to 0. Instead, we're going to make sigma 0, because that is the value of sigma at the imaginary axis. That leaves s to be just j omega. By replacing this value on the characteristic equation, we are going to arrive at a quadratic equation in terms of k, but in reality that can be converted into a system of two equations with two unknowns. All we gotta do for that is separate the imaginary and the real parts, which is done in this line. From that we can get to the value of k of 9/2, which is 4.5 decimal, which is the value of the gain when the function at the critical point, when the transfer function would oscillate to infinity. Also, the value of the frequency at that point is square root of 5 over 2 radians per second, which is just above 1.1 radian per second. With that, we now have gathered all the information required for us to plot the root loci of g of s on the s-plane with a scale of 1 to 12. I have already marked down all the points of interest Here we have the two poles at minus 1, 8 and minus 1. We have our single zero at plus 1. We have the point of breakout at minus 1/2 and the point of break-in at 5/2. We also have the points of intersection with the imaginary axis at plus and minus square root of 5 over 2. We know that each branch starts at a pole and initially it moves towards the other pole. So that gives us this angle of 0. And here it's gonna describe a semicircle centered at the single 0 with radius 1 plus 1/2. So let's see if we can hit the correct intersection point with this ancient technique. Yeah, that was pretty good. Since this branch started at the outermost pole, it's gonna move in towards the innermost 0. So now for the other branch. It moves out towards the other pole. And then it describes the other half of the circle. Since this branch started in the innermost pole and moved initially outwards, it's gonna finish at the outermost 0, which is the 0 at infinity. So this is the real axis, or sigma. This is the imaginary axis, or omega. And that is the root loci of this transfer function on the S-plane.